All right, recording started. Well, I guess I'm not going to worry about seeing people. So are people enjoying the cooler weather?
Yes, times a million.
Very much so.
Yeah, it's about time. It's about time. I am enjoying it too. I'm a little chilly this morning, but I'm not going to complain. Okay. Oh, maybe it would let me see people because I didn't have my video on. Okay, that would explain it. My video was on. I see everybody's static cards and avatars. All right, I'm gonna go back to sharing the screen. I want to get through this today, so um, buckle in. And if you have a question, if a question comes up, holler. Don't be bashful about hollering. I'll try to open the chat. I'm closing lots of my windows, so Zoom is about the only thing I see. Um, don't be bashful about hollering and making me stop. So these are the three things I want to talk about today before we can make this pivot to statistics. And I think you can tell that I'm eager to make that statistic or that pivot. These are three continuous random variables. And what I want to do is I want to, I've talked about each of these briefly. So I think except for the exponential, which I keep confusing with the Poisson, and you'll see why. But I want to go over these pretty quickly and do some examples. Go through some examples of how they're used, and that's where I want to spend more of my time. And on the way, I'll show you some R commands that allow you to calculate with these. But before I do that, let me point something out to you. I'm gonna stop sharing this and go to my camera. So um, in your textbook, so here's the Navidi textbook. And let me do something here. Put color into my camera. So here's the Navidi textbook. You can see nice and green, got the yellow stuff. In classical statistics textbooks, like here in the front cover, just open up the front cover here, and there's these tables. Okay. These are tables for calculating as you can maybe look at this picture right here, this picture is suggestive that the table is for calculating areas under a curve. And in this case, it's a normal curve. I think it's a normal curve. Yep, cumulative normal distribution. So this table helps you calculate areas. You need to be smart enough to know what kind of areas you need to calculate to use this table. We live in a new age, and R will be able to help us calculate all this stuff. We're not going to have to use these tables. We're going to be able to use R. Someday, I'm going to spend some time to show you how to use these tables. But for now, let's just assume that we can use R to do everything we need to do. Okay, so there's a table here. This table is for, oh, it's a continuation of the previous table. At the back of the textbook, there's another table. This one's for what's called the student T distribution. And for different distributions, there's different tables. I'm not going to look for them anymore. So I just wanted to point out that we'll be using R in places that the textbook might tell you to look at a table. And hopefully it'll be obvious how to make the transition between the table and an R command. And by obvious, I mean, hopefully when you see what kind of probabilities you need to calculate, that will tell you what R command you need to use. So hopefully this will become clear as we talk today. Okay. So in general, if you have a continuous random variable, the sample space is some interval.
We
Real-
can't.
Oh, you can't see it. I'm not. Oh, good. Thank you. Thank you for hollering out. Just what I asked you to do. Okay. So in general, when you've got a continuous random variable, and I'm abbreviating here for speed, you have a sample space that is an interval of real numbers. Okay, it's a continuum. And then you have an associated probability density function. P of x, and it has the property that P of x, is always bigger than or equal to 0 for any x in your sample space. And that the integral from minus infinity to infinity of P of x dx is 1. And so with continuous random variables, what we're interested in is calculating the probability that our random variable falls within an interval. With discrete random variables, we are interested in the probability that our random variable equaled something. Continuous random variables, it's different, where we want to know the probability that our random variable falls within an interval. And the way we calculate this is with an integral. Okay. So super important for us. These are defining characteristics that are of theoretical interest to us, but for all intents and purposes, this is interesting to us. And so if you think back to the table that I showed you at the start of class, when I pointed out that it looks like we're calculating an area, this is why. Probabilities are areas under probability density function. Another thing that we use with continuous random variables is a thing called a cumulative distribution function. Abbreviated CDF, or just CDF. Oops. That makes me want to say that the probability density function is often abbreviated as a PDF. Okay. With a cumulative distribution function, it's a function f of x that represents the probability that our random variable, its value is less than or equal to some x. Okay. So these x's are the same. So notice this is a one-sided interval, and this down here is a two-sided interval. So from the perspective of the definition of a probability, you can think of there's a minus infinity there, because the way we calculate a cumulative distribution function is we calculate that improper integral, the integral from minus infinity to x of our PDF. So today, for each of these distributions, I'll make sure that I talk about its density function, its cumulative distribution function, and we'll calculate some probabilities for each. Okay. Uniform. I've already talked about this, so bear with me. For a uniform distribution, you've got a sample space that's a bounded interval. It can't be a half infinite or an infinite interval. It has to be bounded. And if our random variable is distributed normally or uniformly, on omega, we write this. So here's some new notation for us. X, and there's a little tilde or similarity sign, or is equivalent to I'll just write it this way. X is equivalent to a uniform distribution on the interval from A to B. Okay. So This is notation that I'll ask you to use a lot. Then what's the PDF? Well, we've talked about this before. The PDF is 0 if x is not in the interval. And if x is in the interval, it's 1 over b minus a. So the graph of the PDF looks like this. Okay, some people call this a step function. And then this height here, of course, is 1 over b minus a. The CDF, well, the CDF, we'll just calculate it. The CDF is an integral of the PDF. So by definition, the CDF is the integral from minus infinity to x of the PDF. So continuing up to the right. Well, the minus infinity here doesn't make sense, or too much sense. Let's get rid of it because everything down here is 0. So if my integrand is 0 somewhere, I can just drop that from the limit of the interval of integration. So I'm going to replace my negative infinity here with a. And then there's the formula for my PDF. I'll pull that 1 minus b over a out. And you get the integral a goes to x of dt. So asking you to call back some of your skills from your Calc 2 class. Using the fundamental theorem of calculus, you see you get this. So the formula for the CDF, the cumulative distribution function, is 0 if x is less than a. Oops. X minus a over b minus a if x is in the interval from a to b, and 1 if x is bigger than or equal to b. I can put an equal there. So if we just take a second, I'm going to copy this here. So come on. It persists. What this graph looks like is this. I'm going to use blue. So that's what the graph of the cumulative distribution function for a uniform distribution looks like.
Dr. Miller, can you go back a page just really quick, please?
Sure.
Thank you.
You bet. You get it, Ashley?
Yes. Thank
Okay.
you.
You bet. So one of the reasons that these CDFs are useful is because if we want to calculate the probability that our random variable falls in this interval, that's exactly this difference in the values of the CDFs. Because this here is the area below B, this here is the area below A. And if we look at something like this, here's A, here's B. If you look at all the area below B, if it's orange, and then you subtract from that the area that's below A, you just get the area between A and B. So that's what's happening, and that's how the cumulative distribution functions are helpful to us. So just a remark on R. If X is distributed according to a random variable of type, and I'm just going to call it type, okay, then D type, the command D type gives you the values of the PDF, and the values of p-type gives you the values of the CDF. Okay, that is, these are what are the patterns of the commands in R to get the values of these associated functions. So think about D for density and P here for cumulative probability, right? P is associated with this here. So p-type is giving you these things. And I'll show you examples of these as we go along. I'll pop in back and forth between my iPad and R. So here, one more thing. So suppose I've got X, it's a uniform distribution function. Ooh, let me redo this. Suppose X is uniformly distributed on an interval from A to B. And suppose C and D are numbers that are in the interval from A to B. And I want to calculate what's the probability that my random variable falls within the interval C to D. So pictures can often be helpful. So I've got my uniform distribution function here. Here's the plot of the PDF. And if I've got a C here and a D here, I want to figure out what's that area. Well, now that I've drawn the picture, you're like, Miller, we know, we see what, right? It's a rectangle. Take the width times the height, D minus C over B minus A, right? Yes, and you're exactly right. But if I use this idea that we can use the cumulative distribution functions, just watch. So f of D minus f of C. So we calculated a formula on the last page that cumulative distribution functions have these values. When C and D are in this interval, then I can plug in. So this would be an X, but my X here is a D. This would be the X, but my X here is a C. So I get these. Common denominator is the same, so I can put this all over the same common denominator and then simplify the numerator, and then you'll see, surprise, surprise, or actually, no surprise, no surprise, that the value of this probability is given by this. Oops. Exactly the height times the width, just like you told me. Okay. So it all works out. But the point I want to make for you is that though the formulas are going to change down here, this idea persists independent of what distribution you have. Okay. For the normal distribution, this formula works. For the exponential distribution, this formula works. Okay. So let's work an example, a specific example, and I'm going to turn the page here in a second. And the example has to do with a spinner. Sometimes when you play a game, you have a spinner, and at the center of the spinner, the spinner device consists of an arrow that's attached to a piece of cardboard with some sort of, I don't know what they're called, kind of a rivet. And that rivet allows it to spin freely. And so spinners have a cool property. They model a random behavior, a random choice, and they model a continuous random choice. And a spinner doesn't favor any part of the circle. Right? So for a spinner, we could say that the sample space for the spinner is the interval from 0 to 2 pi. And we don't need to worry about the fact that 0 and 2 pi are repeated. If we want to be careful about it, we could remove that endpoint. That's certainly fine. First, so spinner, the sample space is from 0 to 2 pi. Of course, even to talk that way, you got to start some place that's 0 and then say, okay, we're going to go around the circle. And of course, this 0 to 2 pi represents the radian measures, right? So the radian measurement going around the circle. So 360 degrees, 2 pi radians. So if our X is a random variable, that represents where the spinner lands, it turns out X is uniformly distributed on the interval from 0 to 2 pi. So what I want to pose this question. Suppose we have an arc on the boundary of the circle. And it has length 0.25 radians. Okay, so maybe like right here. So if you look at that angle that it subtends there, that angle measures 1/4 of a radian. So let's ask, what's the probability that my X lies in that arc? Right? If I spin the spinner, what's the probability that it ends up in that arc? Okay. So the first thing I'm going to do here, I guess, is let's just rename, let's say on this arc, this is the measure 0 and this is measure 0.25. So it's like I'm moving the origin of my circle just over there. So then I can restate that I'm interested in what's the probability that my spinner ends up between 0 and 0.25. And I'll come back to the reason why I can do what I just did. But we have to have some measurements for where the arc is. And in fact, if you want to, you can choose any starting point. So if you wanted this to be 3, and then this would be 3.25, I encourage you to do the calculation and see how it's different. But let's use what I did and calculate this. So by the definition of probabilities of a continuous random variable, this is the integral from 0 to 2.5 of the PDF of my uniform distribution. And the PDF in this case, oops, typo. The PDF in this case is just 1/2 pi. And so doing my calc 2, pull that 1/2 pi out, I get an X from 0 to 0.25. That's the fundamental theorem of calculus. 0.25 is 1/4, and so I get 1/8 pi, which is approximately 0.0398. Okay, so about almost a 4% chance that my spinner ends up in that region. Okay, so this is an example of how we would calculate something. You know, maybe somebody would give you explicitly what these numbers are going to be. But it turns out, if you take A to be any number in the interval from 0 to 2 pi minus 1/4, okay, and this 1/4, I'm choosing it because of this. Okay, and then if you look at the interval from A to A plus 1/4, so this is an arc of length 1/4, right? Just like we assumed we had at the beginning. Then it turns out the probability that X lies between A and A plus 1/4 is exactly the same as the probability that X lies between 0 and 1/4. And this is why we call it a uniform distribution, because the spinner is equally likely to end up in any interval of length 1/4. The only thing that affects the probability of the spinner landing in an interval is the length of that interval. And you can see that from this picture of the PDF. If the probability is the area, the only thing that affects that probability is how long you choose that interval to be. If you shift both of C and D to the right, but keep the distance between them, you're not going to change the area. Shift them both to the left, but keep the distance between them the same, you're not going to change the area. That's the sense in which this is a uniform distribution. Okay. And that's why I could just choose my interval to start from 0 to 25, 0 to 0.25. Okay. I guess I will close this example by saying, how would we use R to do this calculation? Well, we would look here and we'd say, well, we want to calculate these probabilities here. So I told you that we could use the cumulative distribution functions. Okay. The CDF. And in R, the command for doing that is punif. And so to answer this question, we would say, what's the cumulative probability? What's the value of the cumulative probability distribution of the uniform distribution at the right interval, where the parameters of the uniform distribution are 0 to 2 times pi? And then we subtract from that, and I'm sorry I'm so low on the screen. We subtract from that the value of the cumulative distribution function at 0. So let me rewrite this on the next page. The probability that x is between 0 and 0.25 is punif of 0.25 minus punif of 0. I guess let's just be clear here that this should be p times 2 pi. Put that multiplication in there because I think R really likes that. Okay. So these things here reflect the fact that you're doing a uniform distribution from 0 to 2 pi. So you need those in the function. And then these represent the endpoints of the interval that you want x to fall into. So this is how you can calculate this probability using R. Any questions about that? Okay, let's do another example of uniform distribution. So suppose a manufacturing plant has a process for manufacturing bottles of shampoo. And part of the process is that you fill these shampoo bottles. Okay. With about, say, 378 milliliters of shampoo. Okay, the process for filling has some variation. And if you call x the random variable that is the amount of shampoo in a bottle, x is distributed uniformly on the interval from 374 to 380. So let's answer a couple questions about this. What's the PDF for this random variable? The probability distribution function. Well, we know the PDF is basically 1 over b minus a, where a and b are the interval endpoints of the intervals. So we know here our PDF is going to be 1 over 370 minus 374. And or 380 minus 374. So I'll write this down here for memorialization purposes. That's if x is in the interval from 374 to 380. And it's 0 otherwise. So this is our step function, or right. So that's the graph. And right here, this is the height. It's at 1/6 because 380 minus 374 is 6. Right. So now let's look at what's the CDF. All right. Well, the CDF is the integral from minus infinity to x of the PDF. And because our PDF is 0 until we hit 374, I can write it this way. Okay. And maybe we want to just specify that our x is in the interval from 374 to 380. If x were below 374 down here, my probability distribution function or probability density function would be 0, so it wouldn't matter. So that's why I can put that there. Here, if x gets above 380, I guess I end up with 0 anyway too. But here we'll just specify we're being careful. Then on this interval, our PDF is 1/6. Oops. And so do a little calc 2. We get 1/6 times t. The fundamental theorem of calculus here. So there we go. That's the formula for our cumulative distribution function. And if I want to be more careful, I can say this. The cumulative distribution function is 0 if x is less than or equal to 374. It's 1/6 times x minus 374 if x is in the interval from 374 to 380. And then it's 1 if x is bigger than or equal to 380. So the plot would look something like this. Okay. And because of properties of PDFs, all cumulative distribution functions are going to have this property that above some point, they're going to be all equal to 1, or they're going to be approaching 1 asymptotically. So that's the CDF. Let me show you. Let me see here. Let me look at my R. Let me show you how we would plot one of these things just for fun. I'm going to share with you my R. And I need to make the font bigger. Okay, so we're going to plot the CDF that's 1/6 x times or x minus 374. I'm thinking, let me think. Yeah, so this is how we're going to do it. So I'm going to take my x's, and what I'm going to do is I'm going to make a sequence of x's. So there's a sequence command in R. And the sequence, I'm going to say it's going to go from, let's say, 372 to 382. And I am going to have the step sizes, I'm going to make them in step sizes of 1/4. And we'll see the smaller the step size, the denser my curve will be. So I'll let you play with that on your own time. And now y, I'm going to have y be the values of the p-unif, the cumulative distribution function. So I'm not even putting in the formula. I'm going to let R put in the formula. And I'm going to say I'm going to look at the values of my x's of the uniform distribution on 374 to 380. Okay. And then I'm going to plot x's and y's. So this is just going to do a plot of all these ordered pairs. So if you look down here in the bottom right-hand corner, that's the graph that I plotted, I sketched on my iPad. Okay. So I'll just show you what happens if I change this step size a little differently. You see, if I change the step size from 0.25 to 0.5, it plots fewer points. But this is a good way to get a sketch of a graph of a cumulative distribution function in this case. Okay, so the last thing I'll say about uniform distribution. Oh, well, no, let me ask one more question about this word problem. So what range of volumes of shampoo constitute the lowest 25% of the bottles? So from what lowest volume to what highest volume is like the 25% range of all the volumes that you'll find bottles filled to. So since I'm looking at a frequency, I want to know, here's the lowest volume that we'll see in a shampoo bottle filled. And I don't know what the highest volume is. So that's an unknown. I'm going to call that A. But what I do know is I want 25% of all the bottles to fall within this range. And the question is, what is the range? So here I can use the cumulative distribution function, and I can say the left-hand side here is f of A, whatever that is, minus f of 374. And that should be 0.25. But I have a formula for f of A. F of A is A minus 374 all over 6. And I have a formula for f of 374. 374, you plug that back into our cumulative distribution function, you get 0. So now I'll multiply both sides by 6. And I get A equals 375.5. So I can conclude 1/4 of the shampoo bottles will be filled with between 374 milliliters of shampoo and 375.5 milliliters. Okay. So that's another way a problem could be stated, and then how we translate it into a statement involving cumulative distribution functions. Okay, last word on uniform distributions. If X is uniformly distributed on the interval from A to B, then we saw this already. The mean is the midpoint of that interval. The variance is the length of the interval squared divided by 12. And therefore, the standard deviation is the square root of that. It's B minus A over 2 times the cube root of 3. Okay. So that's good to know. Those are we need to know these facts about uniform distributions. Any questions about the uniform distribution? Oh, I see. So, did somebody put something in chat? Oh, that's okay. All right, let's talk about the normal distribution. Okay, so the our commands are going to be this. Okay, dnorm and pnorm. Dnorm is going to be for the PDF, and pnorm is going to be for the CDF. Probability density function and the cumulative distribution function. So normal distributions have two parameters, mu and sigma, and they're chosen, or they're named suggestively. Here, I guess it's worth saying that sigma really should be positive. I have never heard of sigma being negative. Okay. We define a function f of x to be 1 over the square root of 2 pi all times sigma times e to the minus 1 over 2 sigma squared all times the quantity x minus mu squared. And this is for any real number. So a continuous random variable that has this function as its probability density function is said to be a normal, or is said to be normally distributed.
Professor, did we
Yeah.
switch from lowercase p to lowercase f, or am I missing something?
That is perceptive of you. I am referring to this f as a PDF. You can call it p of x if you want. That's not a problem. Just the way that I was writing, the function came before the mention of the PDF, so I just use an f. That's all.
Okay.
So this is a normally distributed with parameters mu and sigma. And we write, so if the continuous random variable is capital X, then we write x is distributed normally with parameters mu and sigma. There's a special case where mu is 0 and sigma is 1. Then we say x is the standard normal. And we'll often write x is the random variable z. So z is a letter that's often reserved for random variables that are distributed according to the standard normal distribution. If you look through your textbooks and you explore the tables of values they have in there, the normal distribution table, I think at the beginning, is called the standard normal. And so it's giving you values for the normal distribution that has value mu 0 and sigma equals 1. That will lead you to ask, well, how do you use those tables in the general case? And I can address that later. But for now, thank God we've got R. We can just use R. So this function here that I call f and Patrick wants to call p, it is indeed a PDF, okay? Because the values of the function are always 0, are always bigger than or equal to 0. And it turns out that the integral from minus infinity to infinity of f of x dx equals 1. Okay. So now is a time when I would spend 10 minutes proving that this integral is equal to 1. But I'm not going to do that. I think I'll just do a screencast because it would take about 10 minutes to prove it. But I'll do a screencast that walks through all the steps because it's important for you to see because it's cool. Integrating this function. Oh God, I don't even want to write it anymore. Oops. It's non-trivial. It's hard to integrate. You can't use the fundamental theorem of calculus. Okay, so there are tricks. And I'm aware of two tricks. The one that I would use says, well, let's take the integral of this thing and square it and show the integral of the square of these things is 1. And then we'd allow it, we'd know that the original integral is 1. And then to do this calculation, we have to use some calc 3 and some change of variables. To polar coordinates. So it gets a little bit deep, but it's pretty. It's not that intimidating. It just takes time. So I'm going to throw that into a screencast so you can take a look at it. But suffice it to say that the integral of this integrand, the doubly infinite improper integral of this integrand is indeed 1. The graph of the integrand looks like this. So this is for mu equals 0 and sigma equals 1. The graph looks something like that. That's kind of a crappy drawing, but it's what's often referred to as a bell-shaped curve. It's symmetric with respect to the line x equals mu. So it's symmetric with respect to this line right here. That is, the stuff to the left of it is a mirror image of the stuff to the right of it. And that's a fact that we use a lot in this class. So the fact that this distribution is symmetric is important to us. Other facts, the mean is mu. The variance is sigma squared. The standard deviation is sigma. And this is why the names of these parameters was suggestive, right? This is a sigma here in this formula because that is the standard deviation. That is the standard deviation squared. That is the mean. Okay. So when somebody tells you I've got a random variable that's distributed normally with parameters 4 and 1/2, well, you know that 4 is going to be the mean and that 1/2 is going to be the standard deviation. Okay. And usually they should write something like this: mu equals 4 and sigma equals 1/2. Other cool facts. I verified this, that the function has 2 inflection points, one at mu minus sigma and one at mu plus sigma. Geometrically, I don't know why that could be important, but it's a good fact to know. And it turns out that this region between mu minus sigma and mu plus sigma is generally an important region too. So just to know that they coincides with inflection points is kind of neat. And then these things outside, these things out here, these are often called tails of the distribution. Okay, so this is the left tail, This is the right tail. Lots of distribution have tails. This is the first one that we've seen that has a tail because this is the first distribution that is doubly infinite. Since it's symmetric, the right tail and the left tail have the same shape. Some distributions, they aren't symmetric. All right, so let's do an example, sort of how we might use a normal distribution. So another manufacturer, yeah.
When the tails aren't symmetric, is that when we start thinking about it with like the left skew and right skew?
Exactly.
Or is that a different context? Okay.
No, that's right. So we'll see some distributions that kind of look like this. And that's a distribution that's not symmetric. It's, it's just, you can't find any place where it's symmetric. And here we might say this is a right skewed distribution because its tail is longer over on the right side.
Okay. Okay, thank you.
And
You said we hadn't seen any tails before. Does the Poisson distribution not have a right tail?
Poisson distribution is not, it is not continuous, but yeah, you can look at it as a discrete random variable and say that it does have a tail because that is an infinite sample space. So you could say that it does have a tail that direction. It just doesn't have tails in both directions. All right, so suppose we're manufacturing something else. Suppose we're manufacturing cereal and filling cereal boxes. The amount of cereal that goes into a box follows a normal distribution with mean that's 15 ounces and standard deviation that's 0.5 ounces. So we can ask the question, what's the PDF? For this random variable. So let's just write this in there to make sure that let X represent the amount of cereal in a box. And then we can ask what's the PDF for X. Oops, knowing that X is distributed normally. With mean 15 and standard deviation 0.5. Well, then the probability density function, is 1 over the square root of 2 pi times sigma times e to the minus 1 over 2 sigma squared times x minus mu, which is 15, all that quantity squared. So that's the PDF. We could simplify a little bit. So this would be 2 over the square root of 2 pi. And then e times, what's 0.5 squared? That's 0.25. So 1 over 0.25 is 4. So 4 and 2 simplify to that. So it looks like that would be our PDF if I did this right. All right. Now in R, if I wanted to calculate with this PDF, I would use the dnorm command, right? And in this case, it would be dnorm x. Then I could say mu, no, it wants mean equals 15, comma, standard deviation equals 0.5. So that's how I could compute values of the probability density function. What's the cumulative distribution function? Well, it's just the integral of the PDF. So the cumulative distribution function is the integral from minus infinity to x of our PDF. And in our case, it's this. And unfortunately, because the domain of my PDF is all real numbers, there's no way I can simplify out that minus infinity. So this is always going to be an improper integral. If you want to use R to calculate this, you use P norm. And in this case, P norm of x comma, you could write it 15 comma 0.5, but I believe you could also write it including the mean and the standard deviation symbols. And it knows what that means. And of course, this is easier for you to understand in the future when you go back and look at your work. So let's calculate the probability of some cereal. So what's the probability? So this is question C. What's the probability that a box of cereal will have between 14.5 and 15.5 ounces, 14.5 ounces and 15.5 ounces of cereal in it. So we want to calculate what's the probability that our random variable is between 14.5 and 15.5. So we can use the PDF or the CDF, the cumulative distribution function. In that way, which by the way, is the integral from 14.5 to 15.5 of our probability density function. But here's where we'll bring in our R. So we're going to calculate the CDF's value at 15.5. Yeah, we're going to, so this is how we calculate the CDF at 15.5. And then we'll calculate the CDF at 14.5. Okay, noting that we have these parameters, they're common between those commands because these tell us which normal distribution, the parameters of the normal distribution we're using. You throw these into R and you get the number 0.6826895. So I'm going to point out that what we just did is that we looked at the special region I mentioned before, and we calculated the area between the mean minus a standard deviation and the mean plus a standard deviation. And we got about 68.26% of the total area under the PDF, graph of the PDF. So this is an important number for us in the course. It's an important phenomena, and this is an important region for us in the course. So just remember that in the future. You might think, oh yeah, we did an example about that. So last thing I'll mention, how are we doing on time? Okay, we're getting to the end. What's the probability that a box has less than 14.5 ounces of cereal? Okay, so on the one hand, you could set up this. That's what we want to calculate, the probability that box has less than 14.5 ounces of cereal, right? And you could throw that into R and say, well, what's this value, right? And we already kind of calculated that right here. We know MATLAB doesn't have any, or R doesn't have a problem with that. But I want to point to some geometry to you, because this is an intuition that we need to develop this semester as well as as we start investigating statistics. Look at the graph at the top of the page where I have that orange region, right? So that orange region represents the area between the mean minus sigma and the mean plus sigma. So in our problem that we're working, our mean minus our standard deviation was 14.5. Our mean plus our standard deviation is 15.5. What we're asking here in this question is, what's the probability that our random variable has a value less than 14.5? Well, that's another way of asking, what's the probability, or what's the area of this tail? So that's what this means. What's the area of that tail? And I want to show you a cool way to calculate it. Since we know that the normal distribution is symmetric, we know that the area of this tail is the same as the area of this tail. We also know that the area under the curve is 1. So the area in the tails, plural, is 1 minus this number we just calculated in the previous part. But because the distribution is symmetric, and this is the area of both tails, the area of one tail is just half that. So there's the number. And if you calculate this out, you get 0.1586553. So you can either do it with R, or you can use geometry to do it. And I'll just repeat, this geometric way of thinking is going to help us. And sometimes the geometric way of thinking helps you figure out what R command to use to answer a question. So keep that in mind. With that said, I'm going to tell you about the last continuous random variable that we'll be interested in. And it's the exponential distribution, the one I always get confused with the Poisson distribution. All right, so if a continuous random variable has a sample space that's the half infinite line, so from 0 to infinity, and a probability density function P of x equals lambda e to the minus lambda x if x is bigger than or equal to 0, or 0 if x is less than 0. We say x, so if a continuous random variable, we're calling it x, we say x is exponentially distributed with parameter lambda. Okay, and we can write x is distributed exponentially with parameter lambda. So if P is the PDF, then the CDF is this. I can let you do the derivation. But the PDF, it's 0. So this is the x-axis, and this is 0. And the CDF is 0 for negative x. But when x is bigger than 0, the graph looks like this. And it has a y-intercept of lambda. So here's a distribution. It's not symmetric. It has one tail, kind of like the Poisson, and it's exponentially decreasing. It also has the property that if you integrate from 0 to infinity, you're going to get 1. No surprise, right? Because I claimed it's a probability density function, but you can verify it yourself using some of your Calc 2 chops. The exponential distribution has a property that its mean is 1 over lambda. Its variance is 1 over lambda squared. And its standard deviation, which is the square root of variance, is also 1 over lambda. And I think you'll see that that's an interesting parallel to the Poisson distribution as well. And in fact, there's a really tight relationship between Poisson processes and exponential processes. I'm not going to get into that. So exponential distributions or exponential processes, I'll say distributions, are often used to model waiting times. Okay, the time between events when they occur, or recurrent events. So here's an example, and so it's kind of an old-fashioned example because I'm old. But there was a day when you could walk around the public and find public telephone booths, and you walk into a telephone booth, you could close the door, and then use quarters to call somebody with this public phone. So suppose that the length of time someone uses a public phone is an exponential random variable. Okay, and we'll measure the length of a phone call in minutes. Okay, and let's suppose it has parameter lambda equals 1 over 10. Okay. So suppose you're out in public and you need to make a call, but somebody gets into a phone book right in front of you. So you arrive at the same time somebody else does at a phone booth, and they get in first. Okay, so what's the probability that you have to wait less than 10 minutes to use the phone? Okay, so let's calculate what the probability is. Well, so we want to know what's the probability that x is less than or equal to 10. So that means that we're going to use the CDF. Well, now that's the integral from 0 to 10 of the CDF, lambda times e to the minus lambda, our variable x dx. And this is an easy integral to compute. I'll go back up to the top here, but so we all have a lot of room. Pull out the 1/10. The integral of an exponential is the integral again. So using U substitution, I get this. So fundamental theorem of calculus, those are the limits of integration. Plug these suckers in, I get negative e to the -1 minus a negative e to the 0. And so that's negative 1 over e plus 1. So that's 1 minus 1 over e. That's approximately 0.6321206. Okay, so there's a 63% chance, about a 63% chance that you'll wait less than 10 minutes. You won't have to wait more than 10 minutes. Okay. So that's pretty good. Just for a note, if you wanted to use R to calculate this probability, you'd use PEXP, because EXP is the way it abbreviates the exponential. P is for the cumulative distribution function, right? And that's what we're calculating with here. And so you say PEXP 10, because that's the value we're interested in here. And then you put in the parameter for the exponential function, which is 1/10. So one last question, then we'll call it a day. I've got 3 minutes. Maybe I can do it in 3 minutes. What's the probability you have to wait between 10 and 20 minutes? So we want to calculate the probability that x is between 10 and 20. So on the one hand, that's the integral from 10 to 20 of our probability density function. You could also couch that in terms of the cumulative distribution function, right? It's big F at 20 minus big F at 10. But using R, that would be PEXP of 20, and then put the parameter of the exponential in there, minus PXP of 10, and put that parameter in there, right? Always making sure you've got the parameters the same, because you want to be using the same probability distribution. So if you do this, you get 0.2325442. So there's a 23% chance that you'll be waiting between 10 and 20 minutes. What's the chance you're going to wait longer than 20 minutes? Well, it's the complement of the probabilities you've already calculated. So here we've got 23.25%. Here we've got 63.2%. So that's an 86.4, almost 5%. So the complement of that is like about 13.5%. So there's a 13.5% chance that you'd wait longer than 20 minutes to use the phone. Okay, and so that concludes what I wanted to tell you about continuous random variables. And I think we're ready to make that pivot that I was talking about to statistics, starting with chapter 1 of Navidi, and we'll bounce around a little bit, but chapter 1's where we'll start. Pay close attention to the idea of sampling and why sampling is important, and sources of variation. All right, so with that, we'll call it a day. Thanks, everybody. Stay safe, stay healthy, stay warm, and I'll see you on Thursday.
Thank you, Professor.
Thank you, Dr. Miller.
You bet.